thing there. So that's a useful thing. This gives you a smooth, takes you, for instance, from a map of the two-dimensional shear field to a one-component map of the surface density smoothed with an arbitrary filter, but it has to have zero total weight. So it's some sort of compensated filter. Imagine something like a Mexican hat, right? And this aperture mass thing, of course, became very, very popular, particularly with the work of Peter Schneider and others. Now, a completely different way of reconstructing the mass density is shown here, where you can take Fourier transforms of the shear field and relate them to the Fourier transform of the mass density. That's the KS93 method. And again, a slightly more generalized version of this is to look at derivatives of the shear. The shear involves itself derivatives of the potential. And so when you start messing around with various combinations of derivatives of shear, what you're doing is combining various combinations of these derivatives of the potential. Right, the derivatives there. And then you look at this for a while and scratch your head, you realize that you can rearrange that in terms of derivatives of the surface density. So there's a one-to-one relationship between this combination of gradients of the shear and gradients of the surface density. Now, if you're just interested in testing lambda CDM, you don't need to go through all of this. You can just work on the shear directly. But what this gave us was something rather nice, which was what we called at the time the rotation test, which was a realization that if you were looking at these gradients of the surface density, but applied a rotation to the shear values that went in, then you would null out the signal, right? And so that is what is being used these days as a great strong test of systematics in the observations. If you see the so-called B modes, which should have been nulled out when you applied that rotation, then you pretty well know for sure you've got a problem in your data. Not seeing them is not 100% reassuring that you don't have problems, but it's somewhat reassuring. So let me say a little bit about the estimation techniques. I've already paid tribute to the stuff that Valdez and Tyson were doing, and then with Squires and Broadhurst we developed a model, a different method, which is I'm very glad to see still in use now. With Jerry Lupino we generalized that a little bit, and what you really want to have, I think, and this is what led to this paper, it's now 10 years old, is to ask this kind of question, right? We know that a galaxy might look like that, the gravitational shear makes it look like that, so if that's what we see, right, what kind of shear, what is the shear that's needed to make it circular? Well, obviously you don't do that with one galaxy, but say you had a whole, 100 galaxies in some little field. The question you want to ask is, what is the anti-shear that I would apply to that to make those galaxies as circular as possible on average? And this is the answer. Basically, there's an operator. You can't, it all gets messed up by the fact that you have finite resolution in telescopes. You have seeing and you have diffraction limits and so on. But what I showed in this paper in 2000 was how, while you can't, if I say, what would this image look like if I anti-sheared it, right, before observing it? You can't tell what the actual full resolution image looks like. But if you ask, what does a reconvolved image, that is to say, an image that you've observed and then you convolve it once more with the point spread function, you can tell what that would have looked like. If you know shear. And I think this is the fundamental way to go forward with the measurements of the shear, that essentially one can develop then a likelihood function for the shear based on any data you like. It doesn't, there's a lot more to the story of how you turn that into optimal estimators and so on. So then we have people testing these various methods and the competitions that I think we're going to hear about, and measuring the performance and so on. These are important ingredients into the figures of merit that people are playing around with when they're trying to decide whether to put money into LSST or JDEM or whatever. Another thing that we're going to hear about from Urosh, and this is very important area, I think, going forward in the future, is the GI effects and how these are going to be dealt with, which seems to require a combination of n-body type modeling as well as empirical analysis. So let me now move on to a sort of whirlwind tour of the last 10 years of Shear. And the original goal was very much focused on just trying to get at the power spectrum or the 2-point statistics to constrain things like sigma 8. Cosmology has moved on considerably since then. We're going to be hearing about efforts to use higher order statistics to break the degeneracy between the various cosmological parameters. The next step is to measure the evolution of the growth, rate of growth of the structure, and get a handle on the equation of state parameter W. And so on. We're also going to be hearing about shear peak statistics, which are a sort of extension of the higher order statistics. So this was where we stood 10 years ago, and there was a remarkable agreement, but look at the scale. We're actually looking at 10 arc-minute scales here. My, how things have changed. Here's all the work that was done in the subsequent decade. And for instance, this combination, 100 square degrees of data, I'll be showing you tens of thousands of square degrees of data later, but I haven't analysed it all yet. And so sort of state of the art of where things have gone. This is, an exciting plot here from the Canada, France, Hawaii Legacy Survey. Very good that the B mode is way down compared to the E mode, but it's not all peaches and cream. It's actually, the B modes are there quite strongly, significantly. I hope we're going to be hearing from Henk, maybe others, as to what the current understanding of those problems is, because they have to be dealt with, and here's what they were getting for the constraints on cosmology. And so various people I've just cribbed from the literature, some people had put together a compendium of everyone's measurements. This is just to give you a sense of, the great number of square degrees, the amount of work, blood, sweat and tears that's gone into analysing these, and looking, for instance, for an assumed omega, at what the amplitude of the mass fluctuations is. There's pretty good agreement. So then going beyond just pinning down those two parameters, looking for dark energy, you need to see the evolution. So these were some of the early and on the left, I think, somewhat surprising results on the evolution. We've just seen very recently the results from Cosmos that are giving evolution, and this, I don't fully understand this plot, but I thought I'd put it up anyway. It's supposed to show that everything is hunky-dory, and I'm looking forward to hearing more about that. And here is the likelihood contours for the standard parameters that Lensing has been tackling for 10 years and showing that, we're narrowing it down. But the salutary lesson, I guess, is over here, is that we've got a lot of competition in this field, which is that the WMAP contours there are really only a little bit larger. In terms of three-point function, again, the Cosmos analysis is very exciting, and we'll be hearing about this. But again, the bottom line is, how much did the degeneracy get broken? Well, you get a slightly different banana, but it's still a banana. And so these are the kind of constraints. So, So we honestly, have a situation where the CMB guys have really stolen the lead on this subject. They're way ahead, I think, in terms of really constraining things. We have independent results from lensing, but they're a lot noisier. But they really, show there's a proof of principle that this is a technique that works, and we're talking about at most 100 square degrees, right? And there's 40,000 square degrees on the sky, and that's obviously where we want to go. The wider areas beat down the cosmic variance, and we'll also be able to look at the power spectrum and other measures over a much wider range of scales. I think that's an area where, at the moment, we're so limited in dynamic range. We need better control of systematics